Welcome students. This is Liza Joseph, Assistant Professor, Department of Applied Electronics and Instrumentation, Rajagiri School of Engineering and Technology. I am here to make yet another presentation on microelectromechanical systems. So, in today's class, I will be discussing about micropumps. So in our last presentation, we did study the introduction to microfluidics. The study of motion of or transportation of fluids and their mixtures at a microscale level is known as microfluidics. Micro devices which are used to transport and store fluid are called microfluidic systems or microfluidic devices. The microfluidic devices handle fluid volumes in the order of nanoliter. Microfluidic systems are used for a wide range of applications, including the biomedical, environmental, automotive, aerospace and defense. The microfluidic devices are also fabricated by micro machining techniques, which we have understood in our previous modules. Design and development of the microfluidic devices are based on the properties and dynamics of the fluids. It also acquires the knowledge about the interaction of the fluid with the material and with electrical, thermal and optical signals concerned. So, a microfluidic system consists of nozzles, pumps, channels, reservoirs, mixers, oscillators and valves in microscales. However, all these parts can be segmented into four main categories for a microfluidic MEMS. The first one is the microsensor, which is used to measure fluid properties like pressure, temperature and flow. The second part is an actuator used to alter the state of fluids, which include microvalves, micropumps, compressors, etc. The third important segment is the distribution channels regulating the flows in various branches in the system. And finally, the system integration, which includes integrating the microsensors, valves and pumps through the microchannel links. And with this introduction, we will move into micropumps. For my presentation today, the following references have been used on micropumps. So let us now look into the features and the types of micropumps. Today I will be discussing about two micropumps. A mechanical machine that moves fluid or gas continuously by suction pressure is known as a pump. Micropumps are MEMS devices primarily used for microfluidic applications. It involves the transport of small quantities of biochemical fluidic samples in the range of nanoliters to microliters per minute. Various types of MEMS-based micropumps are available, out of which the diaphragm-based micropumps are very common. The diaphragm can be driven back and forth to achieve the pumping action. Let us now look into the construction of one such micropump. The most important part of a micropump is the diaphragm. As I said, the back and forth action of the diaphragm is achieved by the application of an AC signal. The material should have high electromechanical properties such as high electrostructive strain, high energy density, and high displacement voltage ratio. One such material which fulfills all these properties is the polymer. And one of the example is the vinylidene fluoride. So more into the construction of a micropump, let us look into the parts and sections of the micropumps. As I've said earlier, the diaphragm forms the most important part of the micropump, followed with a counter electrode, because two electrodes need to make up a capacitor. Between the two electrodes you have the isolation layer, then we have the actuation chamber, the pump chamber, the inlet and the outlet valves, and the inlet and the outlet microtube. The isolation layer is a design criterion and has high impedance between the two electrodes. The micropump, which we are discussing now, operates on the principle of electrostatic actuation, wherein the deformable silicon diaphragm forms one of the electrode of a capacitor. The upward motion of diaphragm increases the volume of pumping chamber and reduces the pressure. This leads to inlet check valve opening, which allows the inflow of the fluid. Cutting off the applied voltage brings the diaphragm to its initial position, causing a reduction of volume and increase in pressure of the trapped fluid in the chamber. The outlet check valve opens to release the fluid. Let us now look into the picture of one such micropump. So here is the picture of the micropump with this layer as the diaphragm. This is the counter electrode, and you can apply an AC signal between these two electrodes. And this segment is the isolation layer. The fluid inlet is through this segment and the outlet is through this segment. Between the inlet and the pumping chamber you have the inlet check valve, and between the pumping chamber and the outlet we have the outlet check valve. By applying AC signal voltage, the diaphragm can be deflected up and down or back and forth. During a positive cycle of the applied signal, the diaphragm makes upward movement. Because of this, a suction pressure is developed within the pump chamber. The pressure makes it possible to open the cap of the inlet valve here and to allow fluids to enter into the pump chamber. So the fluid will enter into the pump chamber. During this half cycle, the cap of the outlet valve is closed. As the cap exists at the other end of the orifice. During negative excursion of the applied AC signal, the diaphragm makes downward movement, causing the cap of the outlet valve to open. The downward movement makes it possible to allow the fluid to pump away from the chamber. So this is how it works. Now this particular micropump has a diaphragm with a square shape with a size of 4 by 4 millimeter and a thickness of 25 micrometer. The gap between the diaphragm and the electrode is 4 micrometer. The actuation frequency is between 1 to 100 Hz. At 25 Hz, a pumping rate of 70 microliter per minute is achieved. Thank you. We'll continue with the next class.